Welcome to This Explainer. Today, we're diving into a massive, honestly urgent wake-up call for EPCs, safety experts, and project planners working in utility-scale energy storage. We're looking at a critical vulnerability in the green energy transition that just isn't getting talked about enough. If you're involved in asset management, engineering, or renewable infrastructure, you really need to pay attention to what the data is telling us about fire safety in modern battery facilities. Let's get right into it. Take a look at this stark reality from our source material. Standard fire safety concepts for containerized installations are hitting a hard limit. Think about what that actually means for your current projects. As utility-scale greenfield sites scale up to these totally unprecedented capacities, the legacy safety architectures we've relied on for years, they're basically being pushed right past their breaking point. We're trying to build the future of energy storage using safety concepts from the past. And as the analysis makes incredibly clear, that equation simply doesn't balance anymore.
Section 1. The BESS scaling boom and megawatt-scale challenges. So battery energy storage systems, or BESS, are absolutely the backbone of the modern renewable grid, right? They store all that intermittent energy from solar and wind. But here's the massive shift we're seeing. These aren't your standard, modest battery banks anymore. They are expanding into unprecedented megawatt-scale capacities. We're talking about colossal, utility-scale installations designed to handle the energy load of entire communities. The sheer scale of what we're building today is fundamentally different from what we were building even a few short years ago.
Mechanically speaking, what's actually driving this growth? Well, we're seeing exponential growth in individual cell capacities, and that's coupled with highly dense pack designs. To hit those huge megawatt numbers, engineers are packing ridiculous amounts of energy into shrinking footprints. But with this incredible density, a really hidden danger is escalating just beneath the surface. When you pack that much potential energy so closely together, the actual physical behavior of those cells under stress changes entirely.
Section 2. The thermal runaway threat and cascading failures.
Let's talk about thermal runaway. This is a rapid, completely uncontrolled temperature increase right at the cell level, which leads directly to cascading battery failings. It's kind of like a single domino falling, but as it falls, it sets off this intense, self-sustaining chemical heat reaction. And because of those highly dense pack designs we just talked about, the intense heat from one single failing cell immediately triggers the cell right next to it. It becomes this violent, unstoppable chain reaction.
And here is the absolutely crucial point. Planners and FECs are severely underestimating how fast these cascading cell failures completely outpace legacy safety architectures. The source material is throwing up a massive red flag here, guys. Once initiated, cell-to-cell propagation can happen in literally a matter of seconds, generating temperatures well over 1,000 degrees Celsius almost instantly. The speed of thermal runaway in a modern, ultra-dense pack is so ferocious that conventional suppression systems just cannot react fast enough, or with enough force to stop it. Basically, the fire just moves faster than the safety system's ability to put it out.
Section 3. Legacy standards hitting limits.
So we absolutely have to ask ourselves, are current NFPA or VDS standards actually keeping pace with this tech? I mean, these regulatory standards are basically the holy grail for project planners. If a system meets these standards, it's generally considered safe, right? But the exponential growth in cell capacities has happened so incredibly fast. The analysis really questions whether these legacy frameworks are genuinely equipped to handle the unique physics of a megawatt-scale thermal runaway event, or if they're lagging dangerously behind the reality of modern battery tech.
Building on that, the source argues strongly that traditional containerized fire protection standards might simply no longer be sufficient for these modern sites. When you have a standard containerized setup, the fire protection was designed for a very specific volume of energy and a specific spacing of cells. But we've completely changed the variables. We've maximized the density. Applying those traditional containerized standards to a cutting-edge, ultra-dense BESS project, it's honestly like trying to put out a modern industrial fire with a garden hose. It's fundamentally mismatched.
Section 4. Managing symptoms versus prevention.
Ultimately, the core issue comes down to a philosophical choice. On one side, you have damage limitation, which is really just managing symptoms. On the other, you have true prevention, which is eliminating the root cause propagation risks entirely. When a thermal runaway event happens in today's systems, our conventional suppression systems often amount to little more than damage control. They don't stop the runaway, they just try to keep the container from burning down the whole facility. But the asset itself, yeah, it's largely destroyed.
The source demands that we move away from merely managing the symptom of the fire and instead engineer solutions that provide true root cause prevention to stop that cell-to-cell propagation before it even starts. Section 5. The engineering strategy gap. So, how do we fix this? The source material lays out a clear pathway for bridging this gap. Step 1, we have to openly acknowledge the hard limits of legacy containerized installations. We need to stop pretending the old way still works perfectly. Step 2, project planners must define 3 critical engineering strategies that are specifically tailored to stop cell-to-cell propagation in modern dense packs. And step 3, aggressively implement these strategies for real-world safety, moving way beyond just the bare minimum of compliance. Look, this isn't just a casual observation. It is an urgent engineering mandate for every EPC, safety expert, and project planner watching this. If you're designing these utility-scale projects, consider this your wake-up call. You can't just check a box on old NFPA or VDS standards and assume your asset is protected from catastrophic failure. The responsibility falls squarely on the shoulders of the engineers and planners to bridge this massive gap between standard regulations and actual real-world thermal safety. Section 6, a new design paradigm? I want to leave you with this really provocative question straight from the source material. Do we need an entirely new design paradigm for thermal runaway containment? If conventional suppression is failing, and legacy architectures are just completely outpaced by modern density, patching up the old system just isn't going to cut it anymore. We might need to fundamentally reimagine how we house, space, and cool utility-scale batteries from the ground up. The exponential growth of renewable energy literally depends on these storage systems being safe and reliable. So it's time to ask if we are ready to abandon the old models and embrace a radically new standard for safety before the next catastrophic failure forces us to. Think about how your next project might need to adapt. Thank you for joining me for this explainer, and I highly encourage you to keep questioning the standards.